Scientists just discovered gravity hitting 0.000 ms2 on Earth, held for exactly 1.0 second, but three unrelated sensors catch it at the exact same time. But it gets worse, because that same 1-second blink shows up inside navigation residuals for craft moving at 7.66 km/s, and the math refuses to forgive it. Every photon hitting an orbiting telescope tonight starts its journey long before cities exist. However, a 1-second geometry error makes that telescope point at emptiness. According to Einstein, gravity equals space-time curvature, so turning gravity off means flattening geometry, and that breaks the rulebook. Here's why. You pause the curve of a racetrack for 1 second, cars keep speed, but the crash hides until the curve returns and the bill arrives late. That delayed bill becomes the nightmare. However, the data looks clean enough to tempt you into taking it seriously. For 6 months, a joint team running a 2026 timing campaign tied to ESA's Plato and a precision gravity lab at JPL tries to explain it away, but each fix creates a bigger contradiction. They blame a clock bug, but atomic timing holds within 1 nanosecond. However, the blink starts and stops like a metronome. They blame local vibration, but seismometers show nothing in the 0.110 Hz band, and the anomaly still lands on the same second across multiple sites. Then they look at the data one last time, and the return edge looks engineered instead of messy, which makes the room go quiet. If it isn't timing drift and it isn't ground noise, what touches gravity for exactly 1.0 second? The team overlays everything, and the overlap refuses to behave like coincidence. A superconducting gravimeter shows a clean drop, a laser interferometer shows a matching strain-like hiccup, and a satellite orbit solution demands a correction of blood 1.2 meters to close. Here's the crazy part. The duration never wanders. 1.0 second, again and again, like something external runs the stopwatch. But physics immediately pushes back, because nothing gets to press a universal button without paying relativity's speed limit. Here's what breaks them. Gravity changes cannot propagate instantly because relativity caps information at c 300,000 km/s. So a global off switch breaks causality. However, a wavefront sweeping through Earth for 1 second fits the speed limit perfectly. That implication rewrites the question in real time. The blink doesn't come from Earth failing, but from something passing through Earth and canceling curvature like noise-canceling headphones cancel sound. If a wave causes it, what does your body feel first when down disappears? Consequences stack fast, but none of them wait politely. Spacecraft guidance takes the first punch, because a craft in low orbit around 400 kilometers relies on continuous curvature, but a 1-second kink shifts rendezvous math by meters at the worst moment. Every accelerometer-based system takes the second punch because phones, drones, and aircraft lose their down reference for 1 second. However, their software still trusts the lie and steers into error. Mission planning takes the third punch because teams running 2026-era close approach operations, like ESA's Hera near Dimorphos, need tight gravity models, and a 1-second anomaly turns margins into guesses. But the strangest part isn't the danger, it's the repeatability, because repeatable anomalies become experiments, and experiments demand an answer. If the answer isn't a wave, what else fakes a wave this perfectly? Not everyone agrees, and the pushback lands hard because nobody wants a new kind of failure mode. Dr. Mara Keene at the Caldera Institute says, "Gravity doesn't blink. Instruments blink. Catch the eyelid." However, the team counters with synchronized timestamps across continents, and the alignment behaves like a fingerprint instead of a fluke. If instruments lie, why do three unrelated systems lie in the same 1-second window? One signal remains unexplained, and it refuses to match any clean story. At exactly 02:17:18 UTC, an underground particle detector logs a sharp burst, but the direction fit points nowhere consistent in the sky. The particle burst shares the same second as the gravity blink. However, it refuses to share a cause, like the universe leaves a calling card but smudges the name. If something pings Earth for 1 second, why does it also toss particles like a warning? The next test rides on a timing monster, ESA's Plato, sitting in the 2026 launch calendar because Plato turns thousands of star transits into precise clocks. A 1-second distortion shifts a transit edge like a stolen heartbeat, but a sky full of clocks makes the trick hard to hide. Plato either confirms a passing wavefront, or it forces physics to rewrite its own instruction manual. But before the sky test lands, gravity goes quiet for 1.0 second in the only place that matters to you, right under your feet. When gravity vanishes, do you rise, or does Earth drop away from you? Now the thought experiment stops being cute and starts being personal. Gravity stops, and you lose contact first, because the normal force vanishes, but your momentum keeps moving like it never heard the news. At the equator, Earth spins you at about 465 mph, so you keep sliding sideways while down goes silent. You don't launch into space, however you stop accelerating downward by 9.81 ms2, so your stomach feels the signature of freefall without the usual drop distance. In a normal second, gravity pulls you about 4.9 meters downward if nothing holds you up. But now your fall counter reads 0 and your body hangs on its last push. That feels gentle, but Earth under you behaves like a compressed spring that suddenly loses its clamp. If Earth behaves like a spring, what snaps first, rock, water, or air? Earth holds 5.97 satos on 24 kilos of mass, and gravity compresses it every second. But the compression disappears for one beat. The crust and mantle start to relax outward, however rock resists fast motion, so stress spikes instead of flowing smoothly. Faults already near failure take a sudden nudge, and even a tiny slip matters because cities build on margins, not miracles. Deep inside, the core sits near 5,400 degrees, and pressure guides convection that supports the magnetic field, but that pressure briefly loosens, like you loosen the lid on a boiling pot. Gravity returns, but the planet doesn't reset because oscillations keep ringing long after the second ends. If the ground rings, what does the ocean do when buoyancy loses its rulebook? Sea level exists because gravity stacks pressure, but the stack smears when gravity drops to 0. Sound travels in seawater at about 1/500 mph, so the message down disappears, propagates fast through the ocean's bulk, and triggers a global slosh that starts before your brain finishes panicking. Ships lose buoyancy for the second, however they don't instantly sink. They stop getting that upward push and start coasting inside a fluid that no longer pushes up the usual way. Then gravity snaps back, and the ocean recommits to down in a planet-wide slam that turns coastlines into moving targets. That slosh hits ports and undersea cables that carry data like arteries, but the damage shows up minutes later and makes the second feel longer. If oceans slosh, what happens to the air when convection loses gravity? Convection relies on buoyancy, but buoyancy relies on gravity, so smoke stops rising and forms a hovering blob that looks like a glitch in reality. Weather pauses mid-sentence for 1 second, however storms balance on tight energy gradients, and that pause leaves a ripple that spreads into the next hours. Jet engines keep thrust, but intake flows shift subtly when density gradients freeze, and pilots feel a micro-jolt that instruments struggle to classify. Here's the crazy part. The atmosphere stays bound to Earth because gravity binds it. So the instant gravity vanishes, air begins the tiniest outward drift everywhere at once. Gravity returns, but pressure waves keep traveling and nudge systems already close to thresholds. If air and weather change, what happens above the air where satellites survive by constant falling? An orbit works because forward and down cooperate, but gravity stopping deletes the down for one beat. The ISS moves around 7.66 km/s, so it travels 7.66 km in that second, but its path stops curving during the blink. At ISS altitude, gravity measures roughly 8.7 ms2, so the missing inward displacement reaches about 4.35 meters in 1 second. However, docking tolerances measure centimeters, and centimeters decide whether metal kisses or shreds. Satellites avoid immediate doom, but conjunction predictions smear and collision probability climbs in the next passes. Then the biggest trajectory kink hits the biggest moving object you ride every day: Earth's orbit around the Sun. If Earth stops falling toward the Sun for 1 second, where does it actually go? Earth orbits at about 29.8 kilometers s, so it travels nearly 29.8 kilometers in 1 second along a straighter line than its usual curve. That's like driving straight for 1 heartbeat on a curved highway. But instead of drifting 1 lane, you drift 29.8 kilometers through space without noticing it. And that's the kind of scale that turns a tiny event into a cosmic scar. Gravity returns. However, Earth doesn't snap back like elastic. It continues from a slightly different position and velocity, and the orbit inherits a tiny kink that precise tracking refuses to forget. The Moon sits about 384,400 kilometers away, so the Earth-Moon system also picks up a microscopic phase error that ranging can expose down to absurd precision. A 1-second blink leaves a multi-day echo in tracking data, but the echo only matters if you learn what causes the blink. If gravity turns back on, what carries the message without breaking causality? Relativity caps gravity changes at c-300,000 km/s. So any 1-second event draws a hard causal boundary, and that boundary points to a passing front instead of a universal switch. A true global off switch violates that boundary, but a wavefront passing Earth for exactly 1 second fits it cleanly. However, the required amplitude sounds insane, because canceling local down means canceling curvature strong enough to hold oceans, air, and you in place. Dr. Kenji Rao says, if gravity goes quiet, space-time doesn't whisper. It holds its breath. That line turns the hunt into geometry. Something sweeps by with a 1-second thickness, and it leaves fingerprints in timing delays across the globe. If the duration acts like a ruler, what size does 1.00 second imply? 3 culprits compete, and each one sounds like a villain with a math degree. Mechanism 1 uses a scalar field pulse that temporarily lowers effective gravity, but it must rebound without leaving permanent drift, which forces the pulse to look unnaturally clean. Mechanism 2 uses exotic negative energy that cancels curvature. However, quantum constraints fight stable negative energy like the universe enforces a credit limit. Mechanism 3 uses a topological defect, a seam in spacetime, that sweeps through and briefly runs different physics in a thin slab, and that slab leaves a crisp start and stop like a blade. Each mechanism predicts a different fingerprint in timing shape and geographic delay, and that fingerprint turns Earth into an instrument instead of a victim, but only if you catch it cleanly. If 1 second maps to a physical thickness, how thick is the thing that hits us? Now the scale moment locks in the terror. If the disturbance travels near light speed, then 1.00 second corresponds to about 300,000 kilometers of thickness along its motion. That's like a sheet crossing Earth, but stretched so long it spans a huge fraction of the space between worlds, yet it still sweeps through you in 1 heartbeat, and you only notice because your planet flinches. However, if the disturbance travels slower, thousands of kilometers instead of hundreds of thousands, then the thickness shrinks and sensors can map its edge like a moving storm front, which means you can predict where it goes next. That prediction matters, because the wavefront doesn't just hit Earth, it also intersects lines of sight to distant stars, and starlight keeps score. If starlight keeps score, what signature does a 1-second gravity dip leave in a planet transit? A planet transit acts like a cosmic stopwatch, because the brightness drop has sharp edges you can time to the second. Plato runs as a timing monster in the 2026 era, so thousands of transits become a distributed gravity test that no single lab can fake. If Plato catches synchronized plumb-1-torish second edge shifts across a patch of sky, then a moving wavefront leaves a track you can draw like a contrail, and the blink becomes a path you can chase. However, if Plato sees nothing while ground instruments keep blinking, then the eyelid lives inside our machines, and the fix becomes brutally human. What do you think causes the blink? A real space-time wave, or a perfectly synchronized hidden vulnerability in our instruments? Comment question number 1. If gravity stops for 1 second where you stand, What fails first? Your balance, your building, or your GPS? Poll. Which scares you more? Gravity off for 1 second or double gravity for 1 second? Comment. Question number 2. Do you bet on a passing space-time defect, or do you bet on a hidden shared vulnerability that timing finally exposes? Subscribe for the 2026 timing results, because the next dataset either kills this story in public or it eats modern physics alive. Next week, the black hole that's eating itself, but the real cliffhanger lands first. When the next 1 second event hits, does it leave only a number, or does it leave a path across the sky?